Yep, I'm going to talk to you a little bit about NASA's Double Asteroid Redirection Test, otherwise known as the DART mission, and this was the world's first planetary defense test. And the idea here was basically, could we boop an asteroid with a big enough nudge to sort of move it? And the idea being to test the idea of, should an asteroid ever be in danger of hitting Earth, is this a technique that we could use to defend ourselves? And so this was a huge international effort. And so we've just got a list of sort of the places, the institutions that were sort of involved in all of this this huge endeavor. And you can see the ones highlighted in yellow, which I'm associated with, which were the NASA Goddard Space Flight Center and the University of Maryland, Baltimore County. So here's a picture showing you sort of the basic profile of the mission. And so the idea is that we have a binary asteroid. So in other words, we have a big asteroid that's being orbited by a little asteroid. And the big asteroid, or the parent, is called Didymos, and the moon asteroid is called Dimorphos. And the idea was that we would build a spacecraft and that we would launch it and we would try to crash it head on with that moon asteroid. And the aim of that is basically to change the orbit of Dimorphos, the small asteroid, around its parent moon, Didymos. So making that orbit smaller to test if this actually works. Just prior to impact, you'll see there's a little thing called LICIA down there, and that was a small briefcase-sized satellite, or CubeSat, that was launched a few days before the impact, and that would basically was trailed a little bit behind and was able to watch the impact and then the subsequent plume of ejecta that was created by that impact. And at the same time, observatories on Earth were also observing, as well as observatories in space, including the Hubble Space Telescope, the Lucy spacecraft on its way to the Trojans, and the James Webb Space Telescope. So why do we care about asteroids? And why do we care about hitting things? Well, the truth of the fact is that the Earth is basically being hit by things every day. But most of the time, it's not a big issue because a lot of the things that hit Earth are pretty small. And so what we have here is a chart that, this table that sort of goes through the numbers of the size of the types of things that hit Earth, how often they hit Earth, how many of them there are, how big the effect is if they were to hit us, and how many of them we actually know about. So as I said, like pretty much every day we're being hit by things that are sort of a few millimeters to a few inches across, and they're nothing to worry about. You'll probably see them if you go out and you see a shooting star. Now, about once a year, we start being hit by something a bit bigger, about 4 meters, so about 18 feet. That would have a bright flash. It might leave some meteorites, but not much to worry about. There's about 500 million of these, we think, but we know about less than 0.1% of them. Moving up the scale to sort of 25 meters, so in other words, about 80, 90 feet. This is about once every 100 years. This would sort of cause an airburst explosion, could cause widespread injuries if over a populated area. We actually had this happen a few years back. Some folks may remember the Chelyabinsk impact over Russia, and that was an impact within this sort of scale range, and it sort of smashed windows. It was caught on numerous cameras, but it did do some damage and it did cause some injuries. Thankfully, nothing very serious. But it was a reminder to folks of the fact that it could be serious. Now, we think there's about 5 million of these. Again, we don't know very many of these, only about 0.4%. Moving up again, we get to 140 meters. Now, this is about, about 400 feet across. And so when we get into this sort of size, we're actually looking at, this is sort of the same size as our target asteroid for Dimorphos. This kind of impact you'd expect maybe once every 20,000 years. This would create a crater of about a mile across, and this would be deadly if it hit a city. I mean, this would basically wipe out. It would be similar to the effects of a nuclear bomb going off. And we know just under half of these. Going up again, we're getting to 1,000 meters, so about 2/3 of a mile across. This is once every 500,000 years. This would create a crater, sort of about the size of a city, so about 6 miles across. This would be global devastation and possible collapse of civilization. Thankfully, we know of most of these, over 95% of them. And then right up at the top of the scale, we have things of the size sort of 10 kilometers or about 6 miles across. And this is basically, this is bad news, and this is sort of the kind of scale of what killed the dinosaurs. Thankfully, there's not very many of those. Now, you'll see then that at the big end, we have the ones that are very deadly, but thankfully there's not very many of them, and we're not likely to get hit of them. And because they're so big, we're likely to we can spot these very early on, which is why we know exactly where they all are, and why we have that 100% rate of discovery. At the small end, you can see these things are too small for us to actually be able to detect, but thankfully they don't create any damage. They don't really create any noticeable damage. However, you have that really awkward bit in the middle where we know about half of them, but if they do hit, they're going to cause quite a bit of damage. And so here's a map of impacts around the world. And so they're color-coded, and the size of the dots correspond to the size of the resulting impact. And you can see that there's that big red dot, and that is the Chelyabinsk one, which was the impactor I was talking about before, which is about 20 meters across in Russia, and which some of you may have seen in the news. And the impact of that explosion, because it was an airburst, so it basically burst over a city in Russia, would have been about the equivalent of 500 kilotons of TNT. Thankfully, we don't have to worry about these hitting us too often. So again, just to sort of put things into scale, we're going to look at an actual example of a crater on Earth. So this is the famous Barringer or meteor crater in Arizona, and so it's basically about a mile across, just under a mile across. It formed 50,000 years ago and was caused by a 50-meter diameter metallic asteroid. And what we've got plotted over the top of the image of the crater, and you can see the crater in the sort of at the center of the red circle there, is these colored circles, and in that red one basically corresponds to a fireball. So this is essentially as if you were inside that fireball, you would be vaporized. Going further out though, so 10 kilometers, so that's about 6 miles. Going out a bit further, so to about 15 miles, 24 kilometers, you see that there's large animals would be killed or wounded in terms of from the strength of the winds and the force of the explosion. And then even out to about like 25, 30 miles, you've still got at 40 kilometers, you've still got hurricane force winds going. Again, just for some sense of scale, here's a sort of a similar plot right over DC, and you can essentially see that DC itself is completely wiped out in the event of an impact, whereas Maryland and Virginia, the surrounding states on either side, are also significantly impacted. Or again, if we look at Manhattan, for the sort of sales game, you can see that essentially the island of Manhattan is destroyed, and a good chunk of New York would go as well. So just to sort of talk about the size of things in the mission then, we've got a plot here of basically the two asteroids in the Didymos system. So we have the parent asteroid, Didymos, at 780 meters. We have Dimorphos, the little moon asteroid, that was our target, and you'll see the DART spacecraft down at 19 meters there towards the bottom end. And so this sort of should give you just a sense of the scale of this kind of mission and the bodies involved. So what are the sort of techniques that we can use then to actually deal with these things should we have to? So it really depends actually. So there's two sort of factors that are really important to consider. Firstly is how much warning time do you have? How long is it going to be before this thing is going to impact you? Because that has a big impact in terms of being able to deal with it. Because the situation is this: if you know about it a long time before, all you need to do is give it a little nudge and it'll miss Earth by a very large margin. The later you leave it, the bigger the nudge you need to give it. An easy way to think about this is imagine you are on a plane and you're coming into the airport and you're, say, 10 miles away from the airport. Like being off course by about 1 degree actually ends up being like several miles by the time you get down, by the time you get close to the airport. Whereas if you're only a mile away, that 1 degree has a much smaller effect, and you're much closer to the airport. In a similar sense, then, if you're able to give a little nudge when the asteroid is far away, makes it very much easier for you to get it out of the way of Earth. So on this plot, then, we've got these two factors, and we've got warning time running along the bottom, and we've got the diameter of the size of the asteroid running along the y-axis there. And you can see in the blue at the bottom is what's called civil defense, and this is basically a term for evacuation. So this is like the most basic technique, is that essentially if we know somewhere's going to get hit, we just move everybody out of there, make sure they don't get hit. The next sort of size category up, we see something called kinetic. And so this is basically hitting the asteroid with something. And that can break down into one of two forms, either kinetic deflection, so in other words, space snooker, you try and hit it and you try and push it off course slightly so that it misses Earth, or kinetic disruption. You're basically trying to hit it with something and you're trying to break it up into several pieces. Now you'll see along similar sizes but with a longer warning time, is what you call the tractor method. And here what you do is you're sending out a spacecraft and you still want to give it a nudge, but this time what you're actually using is the mutual gravity between the spacecraft and the asteroid, and that's very tiny, but if you have enough warning time, it doesn't matter that it's very tiny, it will still be enough to give that asteroid just that tiny nudge to push it out of the way of Earth. Then we get up to when we get to either very big asteroids or very short timescales, we get to the nuclear option. Some of you may be thinking of Armageddon or Deep Impact for those films. So again, the nuclear option again breaks up into two forms. That's either nuclear deflection, so using a nuke to sort of push the asteroid away, or disruption, trying to blow it up. And so again, here's just another sort of plot that shows you this. And then it shows you this third method, this other method as well, called ion beam deflection. And here again, what you're doing is, if you have plenty of warning time, you send a spacecraft that has an ion source, like ion engines, for instance, and you fire the ions, so these charged particles, at the asteroid, and it gives it, again, just the tiniest of nudges, but that might be all that's needed. So planetary defense then needs to be an organized endeavor, and so there actually exists then this Planetary Defense Coordination Office, and their task is broken up into these segments that you can see on the diagram here. So first off, search, detect, and track. We have to actually be able to see these things, we have to be able to find these things, know how many of them there are, and so we use ground and space-based observatories to basically find these things. The next thing is that once we've found them, we need to characterize them. We need to know how big are they, how risky are they to Earth, what's the chances of them hitting Earth, what are they made of, how heavy are they, like what's their mass and what damage would they cause, that kind of thing. After that, we sort of get to plan and coordinate. Okay, in light of this knowledge, what do we need to do about it? And then we get to mitigate, which is actually taking action based on our plans. And so far, thankfully, the only thing we've actually had to do is test out defense strategies. And this is where DART comes in, because DART was this idea of kinetic deflection. So in other words, space snooker or space billiards, where you're basically trying to hit the asteroid and push it off course. And finally, after we've done things, we need to assess, see how successful the things that we're doing are. Do we need to change anything? And then you start the cycle all over again. This is sort of part of a larger strategy within the federal government, and also moving up even to the national and international level as well in terms of coordination, because if this thing happens, it's going to be a worldwide threat, not just limited to here. So our asteroid system target, Didymos, was actually discovered back in 1996. So how did we actually find it? So you can see here what we have is an image of two different times, and you can see that you've got pictures of the stars, and the stars aren't moving between the frames, but you can see that something else is. And this is called a blink comparator. So this is actually how you find planets and asteroids within the system. This is actually how Pluto was discovered. You basically take images of the same patch of sky, you make sure you line up the stars because they're not going to move, and then anything that moves within that is something that's orbiting, is the thing that you're looking for. So in this case, Didymos. And so after a bit of assessment, we realized that this was actually a binary asteroid, not just one asteroid. So then the next thing to do was essentially to say, okay, we need to sort of define what it is we want to do and how we know that we've been successful. So, number one requirement, hit the asteroid. Okay, that seems fairly self-explanatory and fairly obvious. Your mission's not going to be much of a success if you don't hit the asteroid. The second one is change the binary orbital period. So we're trying to hit the moon of the binary asteroid system and change its orbit. So the third one is being able to make sure that we can measure the change. And so we want to be able to have, first of all, cause the change of more than 73 seconds and then be able to measure that with an accuracy of 7.3 seconds. And then the last one there, number 4, measure beta. Or in other words, measure the momentum change. Or in other words, how big a boop did we give the asteroid? All of these together will essentially help us determine how effective our defense strategy is, because not only do we need to be able to hit the asteroid, we need to be able to make sure that we can measure after an impact to make sure that we've moved it enough in case anything else, or whether there are any other dangers we need to take into account. So with all of that said, we set off in November of 2021 and to catch up with the asteroid. So you can see here we've got the orbit of Earth in the blue, we've got the orbit of the Didymos system in white, and then you can see the orbit of the DART spacecraft there in the yellow line as it basically leaves Earth and then it's chasing after. And you can see that basically as the Didymos system comes round, they'll basically come right on top of each other, ready for DART to hit that to hit Dimorphos head on in September of 2022. So here is just sort of an animation detailing what the mission was like. Now, the shapes that you've seen of the asteroid so far are not what Didymos and Dimorphos actually look like, because these animations and things were basically all devised before the actual impact. So you'll see that the real asteroids are actually quite differently shaped from this, but we'll be discussing that in a bit. So you can see Dimorphos is there moving around, LYSIA-Cube is released, the DART spacecraft hits, makes an impact, LYSIA-Cube observes the impact and flies off. And you can see now that the orbit of Dimorphos around Didymos has changed, and it's now a bit smaller. In other words, it should have a shorter orbital period because we've basically smacked that asteroid head on. So here is just sort of a diagram showing you an overview of the DART spacecraft. And the DART spacecraft wasn't a particularly complicated mission. It didn't actually have a lot of things on it. The main instrument on it was a big camera called Draco, and its aim was essentially to be able to make sure it could see where Didymos was and know about where it was and be able to target it. Then we also have LYSIA-Cube, the small briefcase-sized satellite we were talking about before. We have an ion engine. We have the smart nav. So in other words, the guidance computer, like you would have on a missile, to make sure that this thing hits its target once it's acquired it. So here we've got an animation of LYSIA-Cube. So about 10 days before the impact, LYSIA-Cube was released from the DART spacecraft. And so it just sort of pops out there. And it starts to sort of trail behind a bit. That's it, they're releasing its solar panels. So the DART spacecraft comes in, it hits the target, Dimorphos, it creates an impact ejector plume, and then that's being observed by LYSIA-Cube as it flies past. And so it makes the observations of that, the impact and the subsequent flash, and then it sends that data back to Earth. So here's sort of a closer view of LYSIA-Cube. So again, it's about a foot long, has 2 cameras on it, and those were basically used for observing the impact. So now we're going to look at a few images of the spacecraft being put together. So the spacecraft was basically built at Johns Hopkins APL here in Maryland, and you can see here this is like sort of the core, the backbone of the spacecraft, and so you've got the fuel and not much else on there. And they're basically sort of starting to put things together. You can see they're starting to add the electronics boxes and things into the spacecraft. And then here they are, they're doing what's called thermal vacuum testing. So when you're building things for space, you need to make sure that they can handle the harsh conditions of space, because they're going to be extreme temperature. There can be extreme temperature changes between being in the shadow and being in the sun. several hundreds of degrees for one. And so you want to mimic those conditions by putting it in a thermal vacuum chamber. So that's basically a vacuum chamber where you take all the air out and where you can change the temperature to mimic the conditions that the spacecraft's going to be flying through. Now, DART also had these giant rollout solar panels. So instead of having rigid solar panels, a technology that's been recently developed and was also tested on the ISS are these big rollout ones. So you basically have like a big paper towel roll that you just roll out once you're in space. But you can see that those solar panels are pretty big when you compare them to the scale of the people. Here we have the Draco camera, the main instrument of DART, being installed on board, and this is sort of a telescope with a camera in it, and it's sort of the main part of this mission, the main instrument. And then we've got LiSACube there, the little briefcase-sized satellite, arriving at Johns Hopkins, and then being attached to the spacecraft. And so the spacecraft is pretty much ready now. So they put it on a truck, and they send it all the way across from Maryland to California to Vandenberg Space Force Base, and then they put it inside on top of a Falcon 9. And so, as we mentioned before, back in November 2021, the spacecraft was successfully launched. Once it gets into space, it has to start looking for Didymos. But Didymos is, as you saw in our earlier pictures, just a dot for most of it, and it's really not until the very final few minutes of the mission that the spacecraft was actually able to see anything other than a dot, if you see here. So here we have an image that sort of charts the time and images of the Didymos Dimorphos system. So 4 hours before, still a dot, 90,000 kilometers away, so about 60,000 miles. About 27,000 kilometers, about 17,000 miles. Okay, at this point now we have 2 dots instead of 1. So we know which dot we're hitting, which is going to be the smaller one. And then finally, when we get to 2.5 minutes, we're actually able to see our asteroids as more than dots. And then the very last image, sort of from about 2 seconds before, the last complete image from 2 seconds before impact, at about 8 miles above the surface there, showing you that very bouldery surface. So again, just looking at some of those images, and a bit bigger, so this is about 4 hours before, you can only see a single dot for the system. We get to about 73 minutes, and you can see there's a big dot and there's a little dot, where the big dot is Didymos and the little dot is Dimorphos. Again, 50 minutes, still dots, and then here we have the final few minutes, and now you can see that these asteroids are not the shape that you saw in the diagrams and the animations that you've seen so far. In fact, it's harder to tell from here, but they're actually M&M shaped. So you've got Didymos down in the bottom left corner there, and the DART spacecraft just sort of flying past it here, and we're showing you the last 5 minutes of the impact, sped up by a factor of 10 until we get right down to the end. And we see Dimorphos, and you can see it's this very rocky pile of material. And then when we get to the last image, you'll see that there's only part of that image, and that is basically because it was transmitting that image and it crashed and it wasn't able to finish sending that last image. Now, normally when you crash, and you lose signal from your spacecraft, you're not very happy. However, in this instance, everybody's really happy because it means you hit the target. And interestingly enough, actually, because APL works in the defense sector as well, they actually have folks who work on missiles, and the people who were building the spacecraft went to the missile folks and were like, can you help us? And they were like, yeah, sure, this is easy. And it was like, can we hit this? It was like, yeah, easy. And so they helped them build that. So here we have folks back on Earth at APL, sort of having a look at some of those first images as they come down from the spacecraft. And here we have a picture showing you Dimorphos and Didymos to scale. And here we have an image of sort of Dimorphos a bit closer up. And so yeah, again, you can see that it's it's not at all smooth, and that it's very bouldery. And actually what we think is that normally when you think of an asteroid, you think of like a monolithic big rock, or sometimes as they're jokingly referred to as space potato. But what we see here is actually something that's more akin to a bag, basically a bag of pebbles held together loosely by gravity. And this is what's referred to as a rubble pile asteroid. And the fact that this is not a solid rock will actually have an impact on the way that the momentum transfer happens, and we'll be talking a little bit more about that later. So here in this image you can see that you've got them, sort of looking head on And you can see that there's a terminator like you would see on the moon where some of the asteroid is in shadow. Now, because this is a moon asteroid, there was actually some light that was reflecting off the parent asteroid and then illuminating the dark side. And if we actually increase the brightness contrast on this, you can actually see the dark side and overexpose the bright bit and see the rest of the asteroid. And we call the light that was coming from Didymos was called Didymos. So here we have the last complete image from 2 seconds before the impact. And again, you can see this very bouldery surface. And we've got a composite image here. So you'll notice in this composite image that the material right at the center is very sharp, whereas the stuff close to the edges is a bit blurrier. And this is because this is essentially putting together the last 10 images. So the images that are further away are lower resolution because you're further away, whereas the images that are closer in when you're at the target site are higher resolution, and that's why you get that effect. So to help with the analysis, scientists have named a lot of the rocks and features on Dimorphos. Now, a lot of these will no longer be where they are now, but interestingly enough, and with a suitable sense of humor, the boulders and features on Dimorphos have been named after percussion instruments. The bodhrán, for instance, is an Irish drum used for traditional music in Ireland. And so you can see here that the DART spacecraft, so what we've got is like a sort of zoom in of the target site, and here hit in between these two boulders. So bodhrán and Atabake. And again, here's just sort of a more 3D view of the way that the angle that the spacecraft came in and hit, and you can see it pretty much hit head on in terms of into Dimorphos' surface with a model of the surface there. Now, as we mentioned before, the DART spacecraft wasn't there by itself. Just prior to impact, it had released the LICIACube spacecraft to observe the impact. And so in this animation, you can see images from just before, and that's where it says T minus. So that means minus however many seconds before impact, and when it goes to plus, it's after the impact. And you can see that when you get to 0, you get that bright flash from the impact, and then you can see that there's an impact plume. And this is essentially LICIACube's view as it's flying in towards the plume. Once it got a bit closer, you see it got this image, and you can see that this ejector cone is very complex, and you can see it has tendrils and knots, and it's not a smooth cone. In the animation that we showed earlier, we saw what looked like a very smooth cone, and often with impacts that is what you get. But here you have this very complicated, knotty, tendrily thing that almost looks like a creature in terms of its complexity. And so, bearing in mind what we were saying, this thing is a rubble pile asteroid, and with that, the fact that the asteroid is basically made out of a bunch of rocks, and then on top of the fact that you have the boulders on the surface, as the material is being ejected off, it's sort of interacting with those boulders, and the boulders are sort of blocking parts of the ejector, and that ends up creating these complex patterns that you see on screen here. So you can see sort of the center of the plume is that very bright patch towards the top of the screen, and the bright patch just below it is Didymos, as LICIACube is flying towards it. Here you can see that it's getting a bit closer, and you can see both Didymos and Dimorphos here. This is near closest approach at about 76 kilometers, so about 50 miles away, and you can see towards the middle there we've got Didymos, and then we've got Dimorphos, and you can see again the impact plume. And this is sort of flying down, so this is from in front of the plume. And then here we've got a shot from behind after LICIACube flies past, looking at the impact from the phone. Again, you can see Didymos, you can see Dimorphos, and you can see the impact plume sort of from a side-on view there. We've got some more views here from the green channel, because the image that was used was RGB, so it captured things in color. And here we've got an animation as LICIACube flies past. You can see it gets closer, and then you can see the plume there, and then flies back, and then it's behind. So just to give you a sort of sense of the 3D structure, we have that sort of animation again, but this time what we've done is we've scaled all of the images are the same size. So that means that while LICIACube is further away, images are going to look blurry. As it gets closer, they're going to get sharper. To the right, we have a schematic there showing you the position. So this is like the same, this is like seeing the same point of view as the photograph, but shows you the geometry of the situation more clearly. So you have a yellow dot within a circle, and that shows you where the direction that the sun is coming from. You've got the two ellipsoids there, so the M&M shapes, which are Didymos and Dimorphos. You've got the green where it says NCP, so that's the North Celestial Pole, and then you've got the blue, which is the view that the Hubble Space Telescope had at the time. So if we actually play this animation, you get a sense actually for the 3D structure of the plume. Now you'll notice as well that at times some of the image is obscured, and this is basically to do with the pointing of the spacecraft. As the spacecraft flew past, some of the times it wasn't actually able to maintain pointing at Dimorphos. It was actually pointing the wrong way, so the image shows you that. But what you can also see, oops, we got that there, is with that animation you get a sense of that 3D structure. Particularly if I sort of scan through it like this, you get an idea of the shape of this impact plume. Anyway, okay, so in this next image we again have an image of the ejector plume from in front, but you can see that you have these squares, and what we're doing here is showing you exposing for different brightnesses. As the material gets further out and it gets some of it's finer, some of that material towards the edge is actually a lot darker, so we have to crank up the exposure, whereas the stuff right in the middle is much brighter. So we have to use these different exposures in order to be able to see all the detail. And so you have this this composite image here with the different exposure levels, and that's what those squares represent, where each of those different exposure levels have been used. Now, as well as Da and Licia Q being present at the event was also watched by telescopes from all around the world, and this map shows you all of the telescopes that took part in observing the DART impact and also making observations in the subsequent days, weeks and months afterwards, because after impact wasn't the end of the story. So here we've got an image of the moment of impact from a ground-based observatory, and you can see sort of this plume of material, which is known as fast plume, before the main material comes. And again, from another telescope here, you can see you get that bright flash as it goes past. And this thing was observed all across the world, but what you can start to see in some of these images that was there was a tail. We'll be talking about that in a sec. So, as well as Earth, we also had some other observers in space. So we had the Lucy spacecraft, which is a mission on its way to the Trojan asteroids. We also had the venerable Hubble Space Telescope and the newer James Webb. And what you can see here is actually we're looking at the ejection cone side on, and you can see towards, if you look, there's like a triangle in the top left, so this sector here. Showing you like the side-on view of the cone, and then you've got like the impact there, and you've got a similar view from the James Webb. Now you'll see there's also these spikes in the image, and these are caused by diffraction because of the veins within the telescope optics. So here's just an image from James Webb's view of the impact at the time, and you can see that just that bright flash. Now, in pretty much stating in the hours after the impact, we actually saw the formation of a tail. And so what's happening is that material was basically being blown out of the system by the sun. So light from the sun was strong enough to push smaller dust grains out of the system, and so they form this tail behind Dimorphos. And so the Dimorphos becomes what's called an active asteroid. So an active asteroid is an asteroid that displays similar properties to a comet. So in the same way that you might expect to see a tail on a comet, here we have an asteroid that has a dust tail. Now, unlike a comet, you only have the one tail, because on a comet you'd normally have two tails. You'd have the plasma tail of charged particles, and you'd also have the dust tail. Here we only have a dust tail. So here we've got the view from Hubble, and you can see sort of this is 12 days after impact, and you can see the formation of that tail. And then here you can see like a time lapse of the Hubble images, and you can see the formation of the tail, and you can see how it gets longer. And this tail just kept going, and it kept lasting. So 25 days, and then out to 29 days afterwards. You can see here sort of the formation from various observatories, and it just keeps going. 52 days afterwards, 64 days. We just keep going up. 89, 109, 120, 147. I mean, well over half a year, and this thing was still visible. And it's only recently, actually, relatively recently, that the tail has stopped being visible. But the thing is that sort of the impact and looking at the tail is not really the end of the story, because now the science happens. So 2 weeks after impact, we were able to confirm that the mission had been successful, because we'd hit the asteroid and we'd moved it and we changed its orbit by greater than the target from the requirements that I showed you earlier. So everybody, so folks were pretty happy. And so this is the DART team here. You might be able to spot me sort of towards the back on the right hand side there. But yeah, this is APL at our sort of one of our first team meetings afterwards, where we started discussing the results. So the question then is, okay, so how did we actually measure that the orbit had changed? So to do this, you can use something called a light curve. So now, as you saw in the pictures from right before, you know that we can't actually resolve Didymos and Dimorphos. They're too far away, so they're just dots. However, what you can do is measure the total amount of light that comes from the system. And because from our point of view, Dimorphos passes in front of Didymos and behind it, we can actually see that as dips in the light curve. So whenever it passes in front, you get a big dip, and when it passes behind, you get a little dip. And because those are regular, and because you know the spacing of those intervals, you can use that to work out the orbital period. So you do those observations before the impact, and then you make more light curve observations afterwards, and you basically see what you want to observe, what shift there is between the before and the after, and that will give you the change in orbit. So here we have the results from 1 day after the test, and it's only a very slight change, but the system was still sort of wobbling and adjusting. You can see that by several weeks after the test, we've got a very significant change in the light curve. And we were able to determine that we had changed its orbit by about half an hour successfully from what it was previously. You can see that by the orbit there compared to the orange one. So the orange one shows where it was, and then the normal colored one shows where it was before the impact. So unfortunately, real light curve data is not quite as tidy as what you saw there. It's a bit messier. However, it's still good enough for us to be able to determine things. And so, but these aren't the only methods that we can use to check the position of Dimorphos around Didymos. We can also use radar. And so we can shoot a radar from Goldstone and then use the Green Bank telescope to detect that radar bouncing off it. And so here you have a radar reflection and radar images of Dimorphos, and you can see we've got, Didymos there, and you can see that bright patch, which is the radar reflection of the asteroid. We also get a radar reflection of Dimorphos, highlighted in the little green there. And because we know where it should be, so in other words, in its original orbit, it would be where the teal circle is, but when it was measured, it was where the green circle is. We know, again, that we have successfully changed the orbit. And so again, here we just got a few more radar images just showing you those detections. So we know then that before the impact, 96% of the reflected light, was due to Didymos. But afterwards, approximately 2/3 of the reflected light is due to all of that material, which was out there in reflecting sunlight. Now, to analyze this and to learn what this system is made of, we can use what's called a spectrum. And this is where we basically look at light and we see how much light there is at different colors. In this case here, we're looking at light between 0.7 microns and 2.5 microns, where that's the wavelength or the color of the light. And you can see then that you have more light at certain wavelengths and less light at others, and that basically tells us about what these asteroids are made of. And so we did a before curve and we did an after curve, and we compared them, and we can see that although there's a difference in the brightness, the fact that the shapes where the dips and the peaks are similar tells you that the ejector material are similar. So in other words, Dimorphos, which is what the ejector is all made from, is probably made of similar material to Didymos. So again, just for sense of comparison, Dimorphos is Dimorphos, and it was about the size of the VAB. So this is the Vehicle Assembly Building at NASA's Cape Kennedy Center down in Florida, where they launch it, and the asteroid was basically about as big as that. In terms of the length of the tail that we saw before, it would have stretched this far, around 3/4 of the way around the world, if you were to basically wrap it around Earth. and it would have filled about 60 rail cars worth of material. So what's the next stage in the science? Well, we want to know about the ejector and how much material came off, because that tells us about what the momentum shift was, in other words, how effective the boot was. And so we need to know the direction of the ejector, we need to know how fast it was, we need to know how much there was, and then all of those combined gives us the momentum. So why do we care about how much ejector came off? Well, we care because if you get ejector from an impact, that ejector basically gives an extra push in the opposite direction. So it acts like a little rocket engine, and the more ejector you get, the bigger the push, as you can see in the animation that we have here. So the case on the left, you have no ejector. So in other words, the momentum in is the same as momentum out. Basically just like if you were playing snooker, pool, billiards, that kind of thing. However, once you get the ejector, you can see that you get a bigger boost and you get a bigger nudge. And because of the rubble pile nature of Dimorphos, we think that's why we got more material. And so you can see that the dart impact sort of falls in between some ejector and lots of ejector categories. And we have the momentum enhancement factor of 1, that's basically momentum in the same, that's the same as like snooker. And then you've got the fact that we have material for the dart one. So you can see that it was a very significant impact with a significant nudge in combination with the ejector. So we were able to do lots of good science from this, but the science is not finished, and we're sort of still ongoing with the investigations. So we do things like creating models now, impact models, where we can make computer simulations of the impact and make simulations of the resulting plume. And again, you can sort of see that we're able to represent some of the complex nature of that ejector plume in those simulations. There's also a follow-on mission which was launched last year called Hera. And so it's on its way, and it's going to rendezvous with the DART system, and it's going to stay this time to sort of observe and see exactly what state Dimorphos and Didymos are in, and what's happened to the system. Again, to give us just that more information so that we know exactly how effective this thing actually was. And it's also carrying a bunch of CubeSats that will also do different things in terms of investigating the system. Again, so here we have sort of a visualization of Hera and its CubeSats, and we have, again, what people thought Dimorphos might have looked at before we actually hit it. So I'm going to finish off by talking a little bit about my own work in the mission. And so mine was concentrated on that, finding the mass bit. So using those images of Lissicube from the ejector plume to try and work out how much mass came out of the mission. And so you have sunlight, which basically reflects off that ejector material, and we use that with some jiggery science, jiggery pokery to get plume mass. So how do we do that? Well, we have to use something called a phase curve. So the ejector particle basically scatters sunlight, and the way that it scatters light depends on things like its size. So what we have here is we have an ejector particle, and you can see that there's a light source, and that there's an angle between the source and the observer, which is represented by the eye there, and that's called the phase angle. And you can see that as that angle changes, the amount of light that is scattered, represented by the yellow arrows, changes, and we can map that out as a graph, and you can see that on the right there. So where you have brightness versus phase angle. So as alpha increases, that angle between the observer and the light source, for this case, you can see that there it gets brighter. So this thing is scattering more light forward. And so this thing on the right is called a phase function. And because different particles will do things at different sizes, will scatter differently, you can actually use that as a diagnostic. And so what we have here on the on the left-hand side, then is different particle sizes. So you can see that for very small particles, they tend to get brighter as the phase angle increases, and for very big particles, it tends to get dimmer. And so then if we look at the ejector, and we look at images of the ejector, as the spacecraft flew past, it's basically sampling those different phase angles, and that helps tell us about the size of the particles that are dominating. And so we saw that it's actually getting dimmer. So in accordance with the graph that I showed you, that means that we actually have particles on the bigger side, around millimeters in size. So once we have those images, then we actually need to be able to see how much light there is, so that we can then work out the mass. So what we have are models which tell us how much light there is for a given particle. And so if we add up all the light and we divide it by the number of light per particle, then that gives us the mass, if we know what the sizes of our particles. And so that's what we did. Now, one complicating factor in this is that the particles aren't all the same size. What you actually have is a mixture of particles. And so you have small particles, which are very bright, from, if you remember our phase curve, and very big particles, which don't give off very much light, but contribute a lot of the mass. So we have to basically take all of this into consideration in our analysis to work out what the total mass is. But we were able to do it. And so we came up with the fact that the total amount of ejecta within the field of view was at least 1 × 10⁷. So that's a 1 with 7 zeros after it, kilos. Now, why do I say at least? Well, because this is what's called a lower limit. In our assumption there, when we're doing that analysis where we're basically trying to count the light, sum up all the light from all the particles, we're assuming that we can see all of it. But the problem is that if there's a lot of ejecta, some of it can get very, very dense. In those places where the plume is very dense, particularly near the impact site, it might be that the light of some particles is being blocked off by particles in front. This is called optical depth. And so you have to make an estimate, which we were able to do to account for that factor. And if you do that, the mass goes up by about a factor of 77%. But the good thing is we've been able to find out what that is. So anyway, that's enough about me, and that's basically all I have to say about this. So if you have any questions, thank you so much for taking the time to listen to me. I'm happy to try and answer your questions now.